Hey, then welcome everyone. Season 6 of Ithaca, I believe. Um, we are happy to start with Zurab Janelidze talking about relational duality for Barr exact Maltsev. Start
Thank you
when you're
very much. Thank you very much. Thank you very much for the invitation to give a talk at your seminar. It's a great honor, and I would like to share with you some of the mathematics that I did during my sabbatical, specifically when I was visiting Diana Rodelo in Portugal. As you see from my slide, Portugal is a beautiful country, and you probably know that, many of you more than I. But it was a nice mixture of mathematics and the beauty that surrounds the area. But also there was soccer, and usually it happens so that when I visit Diana, there is always soccer taking place, and this time it was quite unusual. Georgian team won against Portuguese team. That's probably never happened before, and it's difficult for it to repeat again. And that game took place just a few days after we convinced ourselves that the following theorem was true. So the goal of the talk is to discuss the theorem that you see on the slide. And the topic originates from a question of whether there is an approach to Barr exact Maltsev categories that is similar to how things that are usually called noetherian forms give you a self-dual way to work in a semi-abelian category. Noetherian forms themselves are not capable, it seems, of expressing the Maltsev property. And so one might look for a different structure that replaces a bifibration. So what I call the form is usually a bifibration whose fibers are posets. And it was also faithful, the functor that forces the fibers to be preorders, but then we also require them to be posets. But here, the things that we need to be posets is a bit more than just the fibers, which usually are the subobjects. We actually need the full structure of being able to compare arrows, and we even need these arrows to be relations. The theorem states in this context that's abbreviated as ARC. ARC stands for Abstract Relational Calculus. It basically states equivalence of conditions that are very similar to what we've seen in the theory of Barr exact categories, but there is some subtle differences to what we're usually used to. For instance, the first term that arises here, that's a bit strange, is that of an accessible relation. So for those of you who are familiar with the context of an allegory, which abstracts the category of sets and relations, you have morphisms in this context that are not necessarily functional, so they don't satisfy the Galois adjunction conditions. And then those morphisms that are functional, that behave like functions, if you compose them with their opposites and you take chains of such composites, these are the things we will call accessible morphisms. But anyway, so the purpose of this slide is not really to explain this theorem in detail. We will come back to this later on. But just to show you similarity with what we are very familiar with in the theory of Maltsev categories. For instance, condition M3 says that there is possibility of permuting congruences, in fact, more generally of symmetric relations that are also reflexive, and then there is this dual counterpart of coreflexive coming in there. And this permutability of congruences is exactly the traditional Maltsev property. And then there is another formulation of it to require that the composite of congruences is a congruence. And then the last one here, which says M6, that says that every relation is difunctional. And the way you prove that every relation being difunctional is equivalent to these is actually not very difficult. just consider the span corresponding to a relation, and the difunctionality of that span corresponds to permutability of its kernel relations. However, in this general setup, we don't want to force relations to be given necessarily by spans of mappings. And then the proof becomes more complicated. And we will look at that at a later stage. So I hope you had enough time to look at this theorem and see some similarities with what you might have seen before. So let me now move to describing more accurately what is an arc. By the way, the photos that you will see on my slides, they're all taken by me when I was visiting Diana. Okay, so an abstract relational calculus is our main context. We call it arc for short. It consists of a poset enriched category that's equipped with an involution. This is also called a dagger. And so basically it's a triple of a category that's whose homesets are posets, and this is an enrichment, and there is the circle. It's an isomorphism of this category and its opposite category. The standard conditions hold for this structure to define an arc. In terms of examples, of course, allegories are arcs. An allegory has just a few more additional properties that makes it behave a bit more similar to relations, let's say, in a regular category. And in fact, there is a nice axiomatic description of those allegories that do come from regular categories. To my best knowledge, the idea of considering relations as the fundamental object for studying categorical structure of various scenarios, specifically of additive categories, was in the work of MacLean. So I think it's in the book on homology where he talks about relations in additive categories. And then these relations also arise in the work of Marco Grandis on projective homological algebra. But of course, in this century, they are quite often appear in the categorical works that deal with physics specifically, but also sub-applications to functional analysis permit consideration of a structure like this. Sorry, I'm a bit frustrated by the fact that the menu pops up every time I want to underline something. I should have prepared my slide a bit better. Okay, so an arc is a category which is enriched in posets and for which there is an involution. Now, we're not just interested to put any kind of axiom on an arc. So an arc itself is useless. We want to put some more axioms on it, but we don't want just any kind of axiom. We want the kind of axioms that are self-dual with respect to the duality we have in an arc. In fact, we have a few dualities, but now we want the full combination of those. So by duality, we mean reversing the direction of the inequality and also reversing the category, switching from C to C up. The axioms of an allegory are not self-dual in this sense. So we cannot just begin with an allegory. That's why we had to begin with something a bit more basic than allegory. And then the goal is eventually to build up these axioms so that we will be able to do the usual things we can do in Barr exact null subcategories. When null subcategories first appeared in the paper by Carboni, Lambec, and Pedicchio, they were already Barr exact. At the end of the paper, they make a note that one can drop Barr exactness and just consider regular categories. And then in a later paper by Carboni, Pedicchio, and Pirovano, they drop regularity as well. And one of the interesting facts about this context was the calculus of relations. It's a beautiful machinery that allows you to prove results in Barr exact null subcategories. So we're now, in this work, we're basically taking the calculus of relations of multiple categories, of Barr-exact multiple categories, and making an adaptation where this calculus, firstly, it appears in an abstract framework, not necessarily in a Barr-exact category. And secondly, all the axioms we start with are such that their duals also hold. And for those of you who might not know what multiple categories are, they are exactly those that for algebraic categories capture this property of existence of a multiple term, a ternary term satisfying the equations you see on the screen. Some examples of Barr-exact multiple categories include, well, all semi-abelian categories are like that, category of groups, rings, Boolean algebras, algebras over a ring, and so on. There are some more recently arising examples. Marino Gran and his co-authors, thanks to them, we can include this fancy example in all of our papers when we want to say how important what we do is. And this is really something very nice. Co-commutative Hopf algebras, they also form the Barr-exact multiple category because they form semi-abelian category. Great. So that is just to give you a background of what is the departure for us. And let me expand a little bit what I said about duality. There are lots of dualities, well, not too many, but at least 3 in the context of an arc. The first one is given by dualizing the category. So if you look at this picture, and then we reverse the arrows in the picture. The other one is reversing the order. And then the third one is doing both. And on this slide, we see some of the important properties of relations and then their corresponding duals. We will say that a relation is injective. So this is the first property here. When R op composed with R equals identity, and the categorical dual, so reversal of arrows dual of that would be that it's surjective. The order dual is still that it's injective because of the equality here. Because we require equality, it means both inequalities. And so if I just reverse the inequality, it will stay equality. But the combination of those two then gives surjective. So injective becomes dual of surjective. It is this duality that we are really interested in. The others are just technical steps to getting here. Then difunctionality is given by this property here. R composed with R op composed with R equals R. And that's a very important property for studying multiple categories. Already in the first paper on multiple categories, it was recognized. And I think that was one of the main ideas Lambeck brought forward, the importance on emphasizing difunctionality of relations. And later, Maria Cristina Pedicchio also made use of this very much in her work on multiple categories. So all relations in the Barr-exact multiple category are difunctional, which means they satisfy that equality. And in this context, this is a self-dual notion. If you reverse things, it turns out that you still get difunctionality. I'm not going to go through the other properties. They're kind of obvious what they should mean. Reflexivity is the usual thing. Being functional means that R op composed with R is reflexive, and R composed with R op is co-reflexive. That would be dual to reflexive. The symmetry is the usual thing, and transitivity is the usual thing. Positive relations come up in the work of Marino Gran and Diana Rodelo. They're very useful in studying these kinds of things. We will use them as well. So they are those relations which can be expressed as S opposite composed with S for some relation S. Then something that we call dicongruence. This is similar property to positivity, except that now our S must itself be a difunctional relation. And then finally, we have the concept of a congruence, And that's when our relation can be written as S opposite composed to S for some functional relation S. So in universal algebraic terms, this would mean that R is really the congruence corresponding to some homomorphism between algebras. These terms will play an important role, but if we need to recall some of them, please let me know, and I'm happy to recall. Some unexpected nice properties arise already in the most general concept of an arc, where we don't have any axioms yet. For example, well, maybe this is not so unobvious. Injectivity of a relation turns out to be equivalent to combination of difunctionality and being split monic, as well as combination of difunctionality and just being monic. And then there is a dual result that surjectivity is equivalent to those properties. Another unexpected result is the following, which actually defines what we will consider as self-dual analogs of regular categories. Okay, so let's look at the theorem and the conditions in it. The first condition says that every functional relation can be decomposed as an injection followed by a surjection. It will force the M and the E to be also functional, but we don't require that in R1. And the second condition, so this, of course, the first one reminds very much of this property that every morphism in a regular category can be decomposed as a regular epimorphism followed by a monomorphism. The second property says that every congruence is the kernel of some surjective relation. And what is quite fascinating here is that just having information about congruences and corresponding surjective relations, you're also automatically taking care of the injective side of the story. So if, yeah, in a sense, maybe this is a reflection of the idea that if regular epimorphisms are pullback stable, then you can prove that the decomposition into regular epi and the corresponding other morphism, that other morphism ends up being a monomorphism. And something like that happens here, although we don't have any pullbacks in this context. R3 is just a dual of R2, and R4 says that we actually get a factorization system where E is the class of surjective functional relations and M is the class of injective functional relations. So in a regular category, this would be regular epimorphisms and monomorphisms. So I find it quite remarkable that R2 is sufficient to guarantee already something as powerful as R4. There are further equivalent conditions one can add to this list. One can talk about a universal surjective relation that determines your congruence and call it the quotient. So that will be the idea of quotienting out a kernel pair in a regular category. And so if you just require that every congruence has a surjective quotient, that's also already sufficient to get all the other conditions. And then there is also the dual property. Okay, so to prove these theorems, you would need two lemmas, and these lemmas are given by the yellow and the blue Lego block. So the yellow Lego block is the following theorem. This theorem is true in any arc. You don't have any additional conditions on the arc, and it kind of almost guarantees half of the theorem before. I'm not going to go through this in detail now, but let me just mention that there are further surprising properties that kind of come for free in the context of an arc that is then used for the proof of the other theorem. And the theorem that follows it is what is responsible for the fact that when you have nice correspondence between congruences and surjections, that guarantees factorizations nicely as well. It's a technical lemma that is responsible for that part of the theorem that I spoke earlier. So let me skip over that as well in light of time. Now we're we're trying to lead to the main result, which is the result I presented earlier. And the central lemma to that result is this one. So we've got here a diamond, and you see I've inserted the picture of an actual diamond because I'm going to refer to that later on as a red diamond. It's a diamond made out of quotients. So pi c and pi d are quotients of congruences c and d. And the lemma says that, first of all, if the join of c and d exists in the posit of congruences, then pi c and pi d will have a push out, and also the other way around is true. So the existence of this push out is equivalent to the existence of the join. And then if the join does exist, it is going to be the kernel of the diagonal of this push out. So if you take the D map and you compose it with D op, you will get exactly the join of C and D. And then also we have these equivalences that specifically that existence of, this join being equal to the composite of C and D implies not only that CD equals DC, but it also implies a Beck-Chevalier property for this diamond. So it implies that this composite, and when I compose something with reversed arrow, it means compose it with the opposite of that arrow by applying the circle construction. So this composite is equal to that composite as soon as the join of C and D equals to the composite of C and D. This is not very surprising for those who worked with multiple categories in the regular context. So this looks very, very similar to the things we've seen there. And now we're back to the theorem that we saw on the second slide, rather. This time, let me say a bit more about the terms involved in this theorem. So the previous theorem, this one, sorry, not this one, this one, we used this theorem to define a regular arc. So we'll say that an arc is regular if R1 or R2 are equivalent to R3 and so on, if they hold. So they correspond to regular categories, but in a self-dual way, so that the axioms are self-dual and are satisfied by the arc of a regular category. And now we need an analogous concept for Barr exactness, and that's given by E1 and E2. So E1 says that every relation that is reflexive, symmetric, and transitive, in other words, every equivalence relation, is the kernel of a surjective functional relation. This very much matches with the fact that Barr exact category is defined as a regular category in which every internal equivalence relation is a kernel pair. But then we also have the dual of E1, which requires every relation that is co-reflexive, symmetric, and co-transitive to be the op-kernel of an injective functional relation. So op-kernel would be the dual construction. If I've got a relation R from X to Y, the kernel will be defined as R op composed with R, and R op kernel will be defined as R composed with R op. Now, interestingly, E2 no longer holds, E1 no longer holds so what I want to say is that E2 does hold for every regular category, but E1 doesn't. And it holds if and only if the category is Barr exact. So we find this phenomenon that the duals of those conditions that do hold for arcs of regular categories, these duals, some of those conditions now end up characterizing the algebraic properties we're interested in, like, for instance, Barr exactness. Okay, so that's what I tried to say here with this remark. Let me also remind you that I will call a relation accessible if it is a composite of functional and op-functional relations, where a relation is op-functional if its opposite relation is functional. And then we have this theorem that we already spoke about, and the most difficult part in this theorem is, in fact, So these implications are obtained by the standard way that we prove them also for regular categories, Barr exact categories. But it's this implication from M4 to M5 that requires different technique to prove. And the reason why it requires different technique to prove is that in our context, relations are no longer given by spans of mappings. And the reason why then we don't want to require that is because its dual would fail. That we would be requiring that relations are also given by cospans of mappings, which is not true. So, by the way, in the theory of allegories, this is called tabulation. So we say that allegory is tabular, but every relation can be decomposed as a composite of a mapping and its opposite. So how to prove that every accessible relation is a composite of surjective relation and an injective relation when I know that congruences permute, when I have the Maltsev property? Well, first of all, why do we want to prove that? In the standard theory of Maltsev categories, we never encounter M5. But here, M5 will be a stepping stone to M6, because it turns out that while not every composite of difunctional relations is always difunctional, it turns out that if you take a surjective relation E and compose it with an injective one, that will always be difunctional. So surjective relations and injective ones are special kinds of difunctional relations. And their composite turns out to be difunctional as well. Whereas in general, composite of two difunctional relations is not difunctional. So if I can prove that every accessible relation is a composite of surjective and injective ones, then I would have proved that every accessible relation is also difunctional. So that's why I need M5. And the proof of that, do I still have a couple of minutes?
Yes, yes, we
Great.
started
Okay.
later.
So the proof of that, interestingly, and I apologize for this colorful picture, the proof of that, interestingly, makes use of a technique from the theory of noetherian forms that there usually we use for proving isomorphism theorems and for getting the connecting homomorphism. But here it will have completely different purpose. So we begin with the pink maps. The pink maps are functional relations and op-functional relations. So here is a functional relation, here is an op-functional relation, here is a functional relation, and here is an op-function. In fact, the op-functional relation goes that way, but its opposite will be function. So all the black arrows that I've drawn now are actually functional relations. In terms of the original data I was just given a functional relation, then an op-functional relation, then a functional relation, then an op-functional one. But the op-functional one is the one that has its opposite functional, so that's why I'm drawing just the functional ones with the opposite direction. We decompose each of them using regularity. We decompose as a surjective relation followed by an injective relation. So we get this picture. So the red maps are surjective maps, and the blue ones are injective ones. Then when we end up in a situation like this, where I have two injective ones going to the same place, I can take their pullback by the dual of the property I showed you about how commutation of congruences forces, how the join of congruences being given by composite forces a certain push out. So in the dual case, we'll get a pullback. And if you recall, I said that Beck-Chevalier is also forced by that Maltsev property. So we'll have a Beck-Chevalier property for this pullback, which means that this composite will equal that composite. Here in the green diamond, I just have a morphism because now they're both in the same direction. So I can just decompose it as surjection followed by injection. And here I will get the push out because they are both surjective. So I can use that push out property. Then I continue this process. So I've got another pullback of injective ones, and I've got a push out of surjective ones. And then I again take this composite and decompose it into surjection followed by injection. And what I do after that is, because of the Beck-Chevalier property, all of these diamonds are such that we can traverse them in either bottom way or top way. So as a result of that, this entire composite, which was my original thing I started with, my original accessible relation that I started with, this entire thing will now equal to this composite, which equals this composite by Beck-Chevalier, and eventually it equals to the composite of this red thing followed by this blue thing. And it turns out that this red thing is actually surjective. And the reason for that is because these are surjective, and the ones that go opposite way, they're injective. But if I opt them, then the one going correct way will also be surjective. So it's a composite of surjective relations. So the red one is surjective, the blue one is injective, and that's the decomposition we were looking for. We were able to decompose an accessible relation as a surjective relation followed by an injective relation. That brings us to the end. On the last slide, I just point out some of the questions one can explore in the future. For example, the links between regular arcs and noetherian forms would be interesting. And also, specifically, it would be interesting if we can go back and forth, because a semi-abelian category is Barr exact and Maltsev. And the question would be if noetherian form can be used to construct an arc that satisfies the conditions we listed in the main theorem, which was this. And this brings my talk to the end.
Thank you very much. Let's thank the speaker. And open up the floor for questions. Feel free to unmute yourselves or raise the hand, up to you. I will start with one. I don't know if it's relevant at all, but I've heard of a notion of regularity for post-enriched categories, but I don't remember the name of the author, someone in Greece. But have you checked if this relates in any way to that? But if you don't know the notion, maybe I can try to find it out.
Yeah, so there is a very standard notion of a regular allegory. Mm-hmm. What you are saying is probably something different. That will probably be an enriched version of regularity when we're doing specific deposit enrichment. I think it will be something completely different from this, because that notion comes from the idea of viewing morphisms as functions, whereas in this work, as in the case of an allegory, we're viewing morphisms as relations. So at least there will be some differences, but maybe even a lot different, because in this context, for instance, we don't have any kinds of limits, and well, except those special pullbacks and pushouts.
I see.
That context, I expect that we would want some enriched limits as well.
Marino?
Thank you, Zura, for nice talk. I think the Greek mathematician you are referring to is Vasilis Aravantinos Sotiropoulos.
Sounds about right.
He was PhD student here in Louvain, so I think it will be interesting to compare with his work about enriched regular categories. I just have a question. You know that I like Gursa categories. Have you looked at this kind of generalization of your work from Maltsev to Gursa? Probably it's hard, but just curiosity.
That's why we had positive relations. We originally, I think, wanted to do something for Gursa, but we felt that there is so much still to be done for Maltsev that before we do Gursa, let's first understand what happens in the Maltsev case. But I do think that it will be possible to capture some theory of Gursa categories using this way. I kind of believe that it will be possible to do that.
Thank you.
Any other question or comment? If not, let's thank Zurab again.